Welcome to the High Voltage AI podcast. This deep dive is part of a week-long series in the High Voltage AI newsletter over on Substack. We're aiming to educate electric utility engineers like you on overhead and underground construction types, why we use them, what makes them tick. Today's Monday, and we're kicking things off by focusing on the small modular reactor engineering revolution and the career opportunities popping up around it. So, yeah, this week is all about building that big picture for energy, especially for utility engineers. Today, small modular reactors, the engineering shift, the jobs. Tomorrow, we'll get into passive safety systems, factory manufacturing, really interesting stuff. Wednesday is grid integration and industrial heat. Then Thursday, advanced materials, controls, construction systems. And Friday, we wrap with a solid career, action plan, skills, certifications, networking. But for today, the mission is, well, why are these small modular reactors such a big deal engineering-wise, a real revolution? And what paths are actually opening up for engineers? Okay, let's unpack this. So if we look back at what some called the original nuclear renaissance, it didn't quite take off as planned. Traditional plants, the big ones, they faced huge engineering hurdles. It really felt like trying to jam these massive and flexible things onto a grid that needed something nimbler. What exactly made those huge 1,000, even 1,600 megawatt projects so incredibly difficult? For the engineers, I mean.
Yeah, you've really nailed it there. It was an engineering gauntlet is a good way to put it, a constant fight against complexity. For those big conventional plants, the field construction complexity was just, well, staggering. Think about it. Trying to get nuclear-grade precision, but you're doing it outdoors. Everything was custom, fabricated right there on site.
Right, so no economies of scale, really.
Exactly. You had this massive scale combined with really rigid sequential construction. You basically had to build Sister A before you could even start System B. Very little parallel work possible. And the quality control needed for nuclear-grade welding, fabrication, doing that outside, dealing with weather, access issues, it was incredibly demanding. And all that directly led to huge schedule risk. 10 to 15-year timelines are common, sometimes longer, and delays just piled up.
Compounding delays. Yeah.
Absolutely. Which brings us to cost escalation, change orders, rework. It wasn't unusual to see costs balloon by 200, even 400% over the initial budget. Just a recipe for overruns.
I remember hearing stories about the rebar placement, thousands of tons of it, needing micron-perfect placement in these huge concrete pours outdoors. It sounds almost impossible. And beyond just the physical build, I imagine the coordination inside, managing all the systems, that must have been a nightmare too.
Oh, absolutely. The engineering coordination nightmare was, you could argue, even tougher than the physical build sometimes. You're talking 50, maybe more, major systems, all needing to connect and talk to each other perfectly. Flawless interface coordination.
SIFI systems. Wow.
And these plants leaned heavily on active safety. That means complex networks. Diesel generators, pumps, heat exchangers, valves, controls, all for emergency cooling. Layers upon layers of complexity.
More things that could potentially fail, right?
Precisely. Plus, the regulatory interface was intense. Constant on-site inspections. Approvals needed at countless stages. They could stop work for months, and then just finding the people. The workforce requirements meant needing a highly specialized nuclear construction workforce, and there just weren't that many of them available.
Right. And I guess the perfect, maybe painful example of all these struggles playing out is Vogtle. The Vogtle lessons, as they say. The sheer scale of the problems there. It's kind of mind-boggling. What did that specific project really teach utilities about trying to build these giant plants?
Vogtle Units 3 and 4 in Georgia, yeah.
Sure.
It's a really stark lesson. The original cost estimate back in, 2009? Around $14 billion.
Okay.
The actual final cost, over $35 billion.
Yeah.
So 150% cost overrun.
Massive.
Wow. 15 years later.
And the original schedule had them coming online 2016, 2017. The actual schedule, they finally started full commercial operation in 2023 and 2024. A full 7-year delay.
7 years.
And the engineering impact behind that? Thousands of design changes during construction, huge amounts of rework, constant battles with field fabrication. It just showed really clearly that these large, custom, stick-built nuclear projects carry these enormous, almost inherent risks. Very hard to predict. Okay, so you have these huge, super complex, high-risk traditional plants. But how does that reality, that engineering challenge, clash with what modern power grids actually need today? Especially with all the renewables coming online.
That's really the core of the issue, the mismatch. Modern grid integration requirements are totally different. Utilities need flexible resources, dispatchable power that can work with renewables, not against them.
Right, filling the gaps when the sun isn't shining or the wind isn't blowing.
Exactly. That means needing load-following capability, ramping power up and down quickly. They also need distributed deployment. Smaller units you can place closer to where the power is needed, reducing the need for massive new transmission lines.
Makes sense.
And utilities want faster development, projects measured in years, not decades. And crucially, lower risk, predictable costs, predictable schedules. That's key for planning and investment.
So how does traditional nuclear stack up against that wish list?
Well, the traditional nuclear limitations become really obvious. They're basically baseload only, designed to run flat out 24/7. Very poor load following. They're highly centralized, huge plants needing huge transmission build-outs. They're inflexible. You can't just build a smaller version for a specific region. And like Vogel showed us, they are high risk. Massive capital investments with really uncertain outcomes. It's a tough sell for utilities today.
Okay, so this sets the stage perfectly for the small modular reactor engineering revolution. It sounds like small modular reactors, or SMRs, are basically designed from the ground up to fix these specific problems. It's like a totally different philosophy, right? Changing how you even think about building a reactor.
Precisely. That's the fundamental idea. The core insight behind SMRs is manufacture reactors like ships, aircraft, or industrial equipment rather than constructing them like buildings.
Manufacture, not construct. That's a key difference.
It's the key difference. It shifts nuclear from being this unique, massive, one-off construction project into something that could be a repeatable, scalable industrial product. Think about like the jump from custom coach-built cars to Henry Ford's assembly line.
Yeah.
It's that kind of revolutionary shift we're talking about. And that unlocks huge manufacturing advantages.
Okay, like what kind of advantages?
Well, first off, you get a controlled environment. The factory, no more battling weather, site access issues, logistical nightmares that plague field construction, quality control's much easier.
Right, indoors, predictable conditions.
Exactly. Then you get serial production.
Wow.
You can actually have learning curves, improve the process with each unit you build. That's impossible with one-off custom builds. You also enable parallel assembly. Different modules can be built at the same time in the factory. And then, critically, you can transport these completed tested modules to the site for relatively rapid installation. It cuts down dramatically on complex, risky field work.
That idea of manufacturing like ships or planes, it makes so much sense. It feels like such a basic shift, but obviously complex to execute. Are companies actually doing this now, making reactors in factories?
They are, yes. The scale up is the challenge, making it economic. But we are seeing current manufacturing partnerships forming. You mentioned Nascale earlier. They're working with Doosan Enerbility, a big South Korean heavy industry firm, for manufacturing their reactor vessels.
Okay.
It involves a global supply chain for various components, but then often U.S. assembly and final testing happens in dedicated facilities here. And the whole process operates under really strict nuclear-grade quality systems. They're using established manufacturing techniques, but with that nuclear level of QA/QC, the big hurdle now is proving the economics at scale.
So the manufacturing shift is huge, but you hear a lot about passive safety being the real enabler here.
Yeah.
How does passive safety make factory manufacturing possible? Is it because it simplifies the reactor so much, gets rid of all those complex active bits?
That's absolutely a critical piece of the puzzle. Passive safety is really the foundation that makes the SMR factory model viable. Think back to the traditional active safety problems we discussed. All those diesel generators, pumps, heat exchangers, valves, controls, all needing power, all needing maintenance, all potential failure points.
Right, the complexity.
Plus complex containment buildings with fans and filters, multiple backup power systems, huge control rooms requiring constant human monitoring. SMR passive safety solutions strip a lot of that away by relying on basic physics, gravity, natural convection, heat conduction.
Okay, how does that work in practice?
Well, for example, natural circulation, using gravity and heat differences to move the coolant so you eliminate the need for big pumps. Many have an integral design, meaning the steam generators are inside the main reactor, vessel, or containment. That gets rid of huge pipes that could potentially break a major accident scenario in older designs.
Interesting.
Often they have underground installation, which adds physical security and also helps with cooling, using the surrounding earth as a heat sink. But the main thing is simplicity. Fewer active components means fewer things can break, less maintenance, and simpler operation.
Can you give a specific example, like Nascale?
Sure. The Nascale technical specifications are pretty illustrative. Each module is 77 megawatt electric. A 12-module plant gives you 924 megawatt electric, so comparable to a traditional large reactor output, but modular. But here's the key. They state no safety-related pumps, fans, diesels, or AC power required for their safety systems to function.
No AC power needed for safety. Wow.
Right. Their emergency cooling relies on natural circulation and can keep the core cool for over 30 days autonomously. No operator action needed, no external power. And that integral steam generator design, it eliminates the possibility of a large break, loss of coolant accident, a major safety concern for older plants. This inherent safety, baked into the physics, is what really enables the streamlined, factory-built approach.
That is genuinely revolutionary from an engineering perspective. But okay, even with these technical breakthroughs, the energy market is tough. New technologies face headwinds. What's the actual market reality for SMRs right now? Early predictions were maybe a bit too rosy. It feels more measured today.
You're right, the initial hype is definitely cooled a bit, but the underlying foundation for growth is still pretty solid. The current market reality shows a really significant global pipeline. We're talking about 47 gigawatts worth of SMR projects being planned or considered worldwide. That requires something like $360 billion in investment.
47 gigawatts. That's a lot of potential capacity.
It is. Now, near-term deployment is mostly focused on demonstration projects running through about 2030. Broader commercial deployment is really expected in the 2030s. The regional focus right now is mainly North America, Europe, and the Asia-Pacific region leading the development charge. And the market drivers haven't really changed. Carbon reduction goals, energy security concerns, and potential uses in industrial heat applications. Those are still pushing things forward.
But there have been setbacks, right? Like the NuScale project in Utah. What happened there?
Yeah, that was definitely a dose of reality. We saw some economic challenges and lessons with the cancellation of NuScale's carbon-free power project in Utah back in November 2023. It really highlighted the cost pressures. The project's estimated cost jumped 53%, from $6.1 billion up to $9.3 billion.
Ouch.
Yeah. And the projected price of electricity for the off-takers rose significantly, too, from $58 per megawatt hour up to $89. That made it less attractive for the utilities involved. So NuScale pivoted. They're focusing more now on international markets and specific niches like powering data centers. It was a clear signal to the whole industry about the absolute need for tight cost control and, frankly, more realistic initial projections.
Okay, despite those challenges, you mentioned North America as a focus. What specific projects are actually moving forward in the U.S. right now? Where might engineers see activity?
Yeah, the current project pipeline in the U.S. has some really interesting demonstration projects underway. You've got X-Energy building their XE100 reactor. These are 80-megawatt electric, high-temperature gas-cooled units. They're planning a demonstration project in Texas, aiming for operation by 2030.
High-temperature gas. That's a different technology.
It is. Then there's TerraPower's Natrium reactor. That's a 345-megawatt electric sodium-cooled fast reactor going in Wyoming on the site of a retired coal plant, also aiming for 2030. What's really neat about Natrium is it includes 1,000 megawatt hours of molten salt energy storage. Basically, giant thermal battery integrated with the reactor.
A nuclear battery. That's cool.
Kinda, yeah. And construction on that Natrium project actually kicked off in June 2024.
So that one's really moving.
It is. Then you have Kairos Power building their Hermes test reactor. That's a 35-megawatt thermal fluoride salt-cooled high-temperature reactor in Tennessee. Should be operational by 2027. And like we said, internationally, NuScale is pursuing agreements in about 12 countries now, so there's definitely global interest picking up steam.
Is the government helping push these forward, financially or regulatorily?
Oh, definitely. There are quite robust federal support programs. The Department of Energy's Advanced Reactor Demonstration Program, or ARDP, is huge. Over $2.5 billion allocated for these demo projects. TerraPower got up to $2 billion of that for Natrium. X-Energy got $1.23 billion for their project.
Wow, serious funding.
Yeah. There's another $900 million specifically for deploying Generation the Third plus SMRs, and $700 million to help build out the supply chain for the high-assay, low-enriched uranium fuel, or HALU, that many advanced reactors need. And the Nuclear Regulatory Commission, the NRC, is providing crucial regulatory support by developing a new licensing framework specifically for these advanced reactors. That federal backing is really vital to get these first-of-a-kind projects built.
Okay, lots of activity, lots of support. Let's pivot directly to what this means for engineers listening. What's the job market look like? What does the Bureau of Labor Statistics say about nuclear engineering jobs overall?
Right, so the BLS, the Bureau of Labor Statistics, gives us a baseline with the overall nuclear engineering employment reality. Currently, there are about 17,200 nuclear engineers working in the U.S. The official growth projection is actually a slight decline, about 1% between 2023 and 2033.
A decline? That sounds counterintuitive.
Well, it reflects retirements from the existing large plant fleet, potentially outpacing hiring for SMRs in the short term, according to their model. But it still means about 700 annual openings each year, mostly for replacement needs plus some growth. The key thing, though, is the median salary, $127,520. That's about 22% higher than the median for all engineers combined. So it's still a very well-compensated field.
Okay, so overall numbers might be stable or slightly down, but what about SMR specifically? Are they creating new kinds of jobs within nuclear engineering?
That's the crucial point. While the overall numbers look flat, SMR-specific opportunities are definitely creating new, specialized niches. We're seeing real demand in advanced manufacturing engineers who understand factory production, quality control for nuclear components, big need there. Also in digital systems. That includes modern instrumentation and controls, which are way more sophisticated than in older plants. And critically, SCADA systems and cybersecurity for these new digital platforms.
Cybersecurity for nuclear plants, yeah, that sounds vital.
Absolutely essential. There are also growing roles in regulatory affairs because licensing these new designs requires navigating new territory with the NRC. And, as projects mature, significant opportunities in international deployment helping set up projects, supply chains, and operations globally.
That's helpful. Could you maybe break it down even further, like specific engineering disciplines, nuclear, mechanical, electrical, what kinds of roles and maybe even salary ranges are we seeing in the SMR space?
Sure thing. For nuclear engineers, the core SMR roles obviously involve reactor physics, thermal hydraulics, safety analysis specific to these new designs. Salaries there typically range from, say, $95,000 up to maybe $180,000, depending on experience and specialty.
Okay.
Mechanical engineers are heavily involved, especially with the manufacturing focus, designing components, developing manufacturing processes, overseeing installation. Their range is often $85,000 to $160,000. Again, experience matters.
Makes sense.
Electrical engineers are key for the advanced systems, power distribution within the plant, instrumentation, and especially those modern digital INC systems, cybersecurity, human-machine interface design. Salaries there run from about $90,000 to $170,000 for engineers with that specialized nuclear systems knowledge. And control systems engineers are critical too, designing the process controls, the safety logic, integrating everything. Similar range, maybe $95,000 to $175,000 for those specializing in these complex safety-critical systems.
That's a really useful breakdown. Now, what I find really fascinating is this idea of transferable skills. It sounds like engineers from completely different industries might actually have a path into SMRs. Can you talk about that, maybe starting with manufacturing sectors?
Absolutely. The potential for manufacturing industry transitions is really strong. Take someone from aerospace, for example. Their skills in precision manufacturing, rigorous quality systems, detailed testing protocols, that's exactly what SMR manufacturing needs.
Right. Very similar demands for quality and precision.
Exactly. The learning curve would involve getting up to speed on nuclear-specific codes, radiation safety practices, NRC regulations, maybe 6 to 12 months of focused training. But their core manufacturing expertise is invaluable. Or think about automotive. Engineers there have lean manufacturing, automation, managing complex supply chains for high-volume production.
Yeah, skills SMRs want to emulate.
Precisely. They need to learn nuclear quality standards, material traceability requirements, maybe 8 to 14 months, perhaps adapting things like Six Sigma for nuclear. But that high-volume production mindset is a huge asset. And even shipbuilding, especially those with experience on nuclear submarines or carriers. They understand large component assembly marine nuclear systems. They could likely transition faster, maybe 4 to 8 months, just adapting their existing nuclear knowledge to commercial standards and civilian regulations.
That's really encouraging for people in those fields. What about engineers already in the power sector, say from fossil fuel plants or even renewables?
Good question. Power industry transitions are also very feasible. An engineer from a fossil plant already understands power plant operations, grid integration, maintenance procedures. Their learning path would focus on nuclear safety culture, radiation protection, specific emergency procedures, and likely getting an NRC operator license if they're going into ops. That might take 12 to 18 months, but their understanding of the utility world is a big plus. Engineers from renewable energy bring different but equally valuable skills. Grid integration, power electronics, project development experience. They need to learn the specifics of nuclear technology, the long-term planning aspects, how baseload power operates differently. Maybe 6 to 12 months depending on their focus, but their experience with the modern grid and clean energy projects is highly relevant.
And what about process industries like chemical engineering?
Yeah, process industry applications are another key area, especially with SMRs being looked at for industrial heat. Chemical engineers have strong backgrounds in process design, heat transfer, complex system safety. These skills map really well to designing and integrating SMRs for industrial steam or heat applications. They'd need specific training on nuclear heat applications, the regulatory side for that interface. Probably 8 to 14 months, maybe some specialized process nuclear training, but their process expertise could be incredibly valuable, especially for projects like the X-Energy one at the Dow chemical plant.
Okay, this makes the career path seem much more accessible. Let's ground this again in those real projects. Can we look closer at X-Energy and TerraPower? What are the tangible opportunities there?
Definitely. Let's take the X-Energy C100 demonstration first. Location is key. It's being built at Dow Chemical's Seadrift operations plant in Texas. Capacity. It's planned as 4 80-megawatt electric units, so 320-megawatt electric total for the demo. Technology. High-temperature gas-cooled reactor using that Trazo fuel we mentioned, pebbles of fuel, coated in layers, very robust.
Okay.
Timeline. Construction, aiming to start 2026, operational by 2030. Investment, backed by that $1.23 billion from the DOE's ARDP program. Application, providing industrial steam and electricity directly to the chemical plant.
So engineering roles there.
You'd see need for nuclear engineers familiar with HTGRs and Trazo fuel, materials engineers working with high-temperature materials like graphite, process engineers figuring out the heat integration with the chemical plant, and control systems engineers managing high-temperature monitoring and controls. Very specialized roles tied to that technology.
Got it. And TerraPower's Natrium.
Right, the TerraPower Natrium demonstration. Location, Kemmerer, Wyoming, on that retired coal plant site, which is interesting itself, repurposing fossil infrastructure.
Yeah.
Capacity, 345-megawatt electric reactor plus that huge 1,000 megawatt-hour molten salt energy storage system. Technology, sodium-cooled fast reactor, integrated with storage. Timeline, construction started June 2024, aiming for 2030 operation. Investment, up to $2 billion from ARDP.
And the impact.
The projected economic and workforce impact is significant for Wyoming. Potentially 2,000 construction jobs at peak, about 250 permanent jobs for operations, and an estimated $4 billion total economic boost for the region. Key skills requirements: there will be engineers familiar with fast reactor physics, handling liquid sodium coolant, molten salt technology for the storage, and energy storage integration. Again, very specific technical needs.
That's fantastic. Real projects, real jobs, specific skills. It really brings it home. So this raises the practical question. How does an engineer, maybe someone listening now at a different career stage, actually get involved? What are the pathways? Yeah, good question. The pathways differ a bit depending on experience. For entry-level engineers, say 0 to 3 years out of school, the education foundation is obviously key. A solid degree in nuclear, mechanical, electrical, or chemical engineering, maybe with coursework relevant to reactor physics, advanced manufacturing, power systems, or process design. Their professional development priority early on should be building fundamentals, nuclear basics, understanding NRC regulations and licensing, quality assurance principles, also getting exposure to manufacturing systems, quality control, lean, maybe Six Sigma, and basic project management. Career entry points for them would likely be roles like manufacturing engineer, design engineer, test engineer, maybe a project engineer supporting a specific SMR module or system.
Okay, what about engineers who are maybe mid-career looking to make a switch, say 3 to 15 years of experience?
For mid-career transitions, it starts with a really honest skill assessment framework. Look at your technical skills, maybe give that 40% weight. Your regulatory knowledge, even if it's non-nuclear, perhaps 20%. Project management experience, say 25%. And relevant industry experience, maybe 15%.
Try quantifying where you stand.
Exactly. Then build a transition strategy. Identify the gaps based on that assessment. Start networking heavily in the SMR industry conferences, LinkedIn, professional societies. Do targeted skill-building online courses, certifications in nuclear fundamentals or regulations, and then position yourself strategically, highlighting how your existing experience translates directly to SMR needs in your resume and interviews.
Makes sense. And for the very experienced engineers, the senior folks, technical leaders, 15-plus years.
For senior engineers and technical leaders, the opportunities shift more towards leadership and strategy. We're talking leadership opportunities in technology development, leading teams, designing the next iteration of SMRs, program management, for overseeing the deployment of multiple SMR units or entire projects. Regulatory interface, becoming a key liaison with the NRC. Or business development, looking at new markets and strategic partnerships. Executive preparation for these roles means having deep industry knowledge, strong strategic thinking, being adept at stakeholder management, and possessing real change leadership skills to help guide the industry's evolution.
Okay, great breakdown of the pathways. Let's try and distill this all down. If an engineer is listening to this deep dive, what's the absolute bottom line for their career prospects regarding SMRs?
Right, the key career realities. Let's summarize. First, market development. Yes, early hype cooled, but that $360 billion global SMR pipeline and nearly $1 billion in U.S. federal demo funding, that provides a solid foundation for real, sustained development through the 2030s. It's happening. Second, engineering demand. Opportunities are becoming more focused, more specialized. Think advanced manufacturing, digital systems, regulatory affairs, international work. And remember, nuclear engineers still earn that significant 22% salary premium over other engineers.
Good point.
Third, technical innovation. This isn't just hype. Passive safety and factor manufacturing are genuine engineering breakthroughs. They directly address the historical problems of traditional nuclear construction and are creating genuinely new engineering specializations. Fourth, career positioning. Engineers getting into SMRs now during this demonstration phase will gain incredibly valuable experience with next-gen nuclear tech. That positions them perfectly for leadership roles when commercial deployment ramps up later this decade and into the 2030s.
Getting in on the ground floor, essentially.
Yeah, pretty much. Fifth, geographic opportunities. There are real projects creating jobs now in places like Wyoming, Tennessee, Texas, plus growing international prospects. It's not just theoretical. And finally, industry maturation. The next 5 to 10 years are critical. They'll really determine the commercial viability and scale of SMR deployment. Engineers developing expertise now gain a significant first-mover advantage in shaping this potentially huge future market.
So here's a thought to leave you with. Think about how your current skills, maybe from aerospace or automotive or perhaps even renewables, could actually be an unexpected launchpad, a way into a technology that might just reshape global power. What new skills will you prioritize to be part of this energy revolution? And just a quick reminder for tomorrow, Tuesday, we'll dive deeper into how those passive safety systems really enable factory manufacturing. We'll look at the nitty-gritty technical innovations and the specific engineering disciplines needed to pull off nuclear-grade manufacturing at scale. If you'd like to leave feedback or have any questions, feel free to reach out to our producer, Julius Guai, on LinkedIn.